All right, so now we have the final talk of the session. This is also a distinguished paper. It is titled Cobble, Compiling Block Encodings for Quantum Computational Linear Algebra. The author of the paper is Charles Yuan. He is an assistant professor at University of Wisconsin-Madison, and he is currently looking for motivated students to work with. And so without further ado, I will let him explain the work.
Thank you so much, Sarah. And hi, everyone. I'm really honored to be awarded for this work. Today, we are going to talk about how to program quantum computers to solve linear algebra problems very efficiently. And so part of what I mean by that is that over the last couple of years, we have seen a blossoming of these quantum algorithms for all sorts of interesting applications, ranging from solving systems of linear equations, solving differential equations, simulating physical particles, and even doing things like statistical regression. Right? So kind of the bread and butter of modern data science, MLE kind of applications. So one thing you may know about quantum computers and quantum algorithms is that they promise asymptotic speedups over what classical computers can do in these applications, up to exponential speedups. And in this case, for something like inverting matrices, solving linear equations, we do get an exponential speedup under favorable conditions. So you can see that it's exponential because the quantum complexity is polylogarithmic in the dimension of the matrix in. That's to be compared with the classical complexity, which is going to be polynomial in the dimension. Right? That's where we get that exponential speedup claim. What you may not know, even if you're familiar with quantum algorithms, is that, believe it or not, a whole lot of other quantum algorithms out there, things like Grover's algorithm for search, that don't look like linear algebra at first, actually can be represented as a specific matrix computation you want to perform. Right? So it kind of gives us a unifying picture of a lot of these quantum algorithms, even though we're not going to have a time to talk about them today. So all of this, great news for the algorithms world, but what does it have to do with programming? Well, one of the things is that, believe it or not, almost none of these algorithms has ever actually been written down as an actual program that could run on a hardware quantum computer. So why is that? Why is this problem so difficult? Well, to see why, let's put ourselves into the shoes of a quantum programmer, open up one of these papers, and look at what the paper gives us. It's not pseudocode, it's not an algorithm listing, it's just math, a whole bunch of equations that take the form of something like this. We want to compute a matrix function, A inverse, e to the minus iat. And what the algorithms paper tells you is all of the math that's necessary to decompose that matrix function into primitive operations, addition, multiplication, these sorts of things on matrices. Right? And eventually, when you get down to the base case, you even have to decompose your input matrix A into things like smaller matrices all the way until you get down into primitive logic gates that will be provided to you natively by the quantum computer. So every step of this process, representing and constructing a matrix and then building up all of these linear algebraic computations, is a programming challenge. And what do I mean by this programming challenge? Well, there is a first problem here, which is the gap in abstractions that we have available to us as programmers. If you wanted to take the paper representation of a quantum algorithm and make it run on hardware, you eventually need to get this thing, which is a quantum circuit, individual logic gates executing on individual qubits in the system. So how can you do this? Well, today, if you are a programmer, you could use something like IBM's Qiskit framework, which is a Python-based framework in which you can just write code that specifies, it lists out every single one of those little squares in the picture there. Right? That is a form of programming that we have today. And it's really nice for a lot of algorithms. But what if I told you that it is possible to build higher level programming abstractions in which you essentially just write the same notation as the algorithm designers intended and leave it to the compiler to automatically generate the actual sequence of logic gates? That would save us a lot of work, and it is indeed what we are trying to do in this work. Right? So that is the first problem here. We want to be able to close this abstraction gap, get the circuit from a suitable high-level language. But even having the circuit in hand is not enough, because we have very small quantum computers. We want to make these circuits as small as possible, as few gates and as few logic gates as possible, so we can run it on the nearest term computers that are coming online. What can you do to solve this problem? Well, today you could take one of these off-the-shelf existing quantum circuit optimizer tools. Right? There are a whole lot of them now in existence. Some of them have been published at PLDI. Our experiments show that given circuits of these applications, they typically see something like a 30% improvement in performance. What if I told you that by exploiting higher level program structure, you can get instead 95% speed up? Now, this is not going to be global for all circuits, right? Generic circuit optimizers don't have program structure. They have to solve a much harder problem. But if we have a suitable high-level language, we can exploit that program structure and get really good speedups, right? So before I continue, I want to spend a quick minute or two getting everybody on the same page as to how these quantum algorithms work. I mean, why should a quantum computer be so good at linear algebra? Well, the short answer is because quantum computers are linear algebra. We've seen so far some definitions of these qubits, right? Quantum analogs of bits. They can exist in these states which are called ket0 and ket1, which are actually just vectors with complex coefficients. Here, ket0 is 1, 0, ket1 is 0, 1. The cool thing about qubits is that they can exist in superposition, so 0 and 1 at the same time. And mathematically, a superposition is just a linear combination of vectors. So we can have two arbitrary complex numbers in those coefficients there. You know, just linear combinations, just some linear algebra, right? So if I have this sort of construct, I can already start thinking about how to generalize this to encode arbitrarily large vectors, not just vectors of 2 elements, but of n elements. There is a rich study of how to do this supposed amplitude encoding step. I won't have time to explain all of this. There's actually a lot of deep theory here. I'll refer you to the paper to see the details, but it is the general idea of how you can represent vectors on a quantum computer using a very small number of qubits. Now, given qubits, what can we do with them? Well, one thing we can do is to measure them. Measuring a qubit collapses its superposition and gives us a classical outcome, either 0 or 1 with some probability. That probability happens to be derived from the square of the norm of the complex amplitude. So negative 1 over square root of 2, norm squared turns into 1/2. Right? So measurement will collapse the superposition of the qubit, making it not quantum anymore. So we don't want to be doing that all the time. Instead, what we want to do are these quantum logic gates, which can manipulate the state of information without collapsing it from superposition. There are a whole lot of logic gates out there. For example, there's a quantum version of a NOT gate. It has a denotation, which is a 2x2 unitary matrix that multiplies by the vector. And in this case, what it does is it permutes the coefficients to turn ket0 into ket1 and vice versa. There are more interesting gates out there that do things like create superpositions, like this Hadamard gate here. And you can even have bigger matrices. So for example, you can do conditional logic. This controlled NOT gate will flip the value of the bottom qubit only if the top qubit is equal to 1. So you can imagine that this ends up being represented as a 4x4 unitary matrix over 2 qubits, length 4 vectors. Right? So that was a lightning-fast introduction to quantum computing. I want to move on to talk about some of the research contributions here and start by covering how we build a language to close this abstraction gap. So what makes representing matrices hard on a quantum computer? Well, how do we even represent matrices on a classical computer? Well, I don't know about you, but when I see a matrix, I probably am tempted to take that matrix and write it down as a whole bunch of floating point numbers represented in my random access memory, right? A whole bunch of arrays. Whether the array is dense or sparse, it doesn't really matter. It turns into a bunch of arrays, and we have all of these nice for loop-based iteration patterns that we can use to perform operations like matrix multiplication very efficiently. You get enough of those, you package them into something wonderful like BLAST and LaPack, you publish it out there, and you get a whole world of matrix arithmetic. Of course, arithmetic whose scaling is polynomial in the matrix dimension in. The whole point of doing it on the quantum computer is to make that faster, right? It's to have this polylogarithmic representation. And we've already seen how a quantum gate, being natively a matrix, ought to be able to do this for us. So whenever we have these matrices, we're just going to write down a small number of gates that implicitly, through their semantics, represent the matrix we care about. And then we're going to have to figure out what the corresponding computation, what the programs are going to look like. All right, and that is going to be the goal of this Cobble system. Figure out the quantum analog of BLAS, NumPy, and such. So let me show you very quickly what it is like to program in this world. We're going to take that kind of mathematical notation that you might find in these algorithm papers, and the compiler will generate for us the circuit given that program. Right? Just a couple of observations about the circuit. You can already tell it has some compositional structure. There's some sub-circuit corresponding to A for B, and eventually you get down into these primitive logic gates. In this example here, they're X and Y. You can't go break them down any further. They're just going to be the native operations that the device already gives you. All right. So rather than harping on about the technical design here, I want to motivate the design by asking an open-ended question. Which matrices do we hope to be able to efficiently encode as programs into a quantum computer? It's a very open-ended question, and indeed the theory community spent like 10 years trying to answer it. They finally managed to do it in around 2019, where there were 2 landmark papers that were published, showing 2 apparently contradictory results. The first one is that there is no hope of doing this for arbitrary dense matrices. You cannot take arbitrary matrices and encode them efficiently into a quantum computer. But the dual of this is if your matrix has structure, if it's particularly sparse, particularly repetitive, built up from smaller matrices, then there is a constructive way of actually doing this. All right? So that is going to be the basis, ultimately, of our language design. Of course, we want to use these gates, those matrices, to represent the matrices we care about. I mentioned this unitary thing, right? The semantics of every gate is a unitary matrix. What is a unitary matrix? Well, it's some kind of linear, norm-preserving, diagonalizable eigenvalues unit, that sort of thing. But the thing that's interesting about it is that unitary matrices are not closed under arithmetic operations like addition. Some of unitary matrices is not necessarily unitary. That is a massive pain if we want to encode arbitrary matrices that we care about in this framework. Fortunately, once again, we have an answer from the theory community. It's called a block encoding. Right? So what a block encoding is that given an arbitrary, possibly non-unitary matrix A, we're going to shove it into the top left block of a bigger matrix, B of A, such that the other 3 blocks of the matrix are allowed to be arbitrary, as long as this whole big matrix is unitary. This is always possible, subject to a mild condition that the entries of A are not too big. If they are big, you have to divide the whole thing out by a number alpha, which is called the subnormalization. Remember that term. It will come back, subnormalization. Right? It's definitely related to that. So in this case, the lower bound here is going to be the spectral norm of A. So one cool thing that we can do with a block encoding is that we can perform all the matrix operations that we want, for example, matrix vector multiplication. If we have a block encoding of the matrix A and an amplitude encoding of the vector x, we want to get an encoding of the vector ax. We can do this by taking that block encoding and applying it as a circuit to the state x, along with a couple of extra qubits, and this will give us a resulting superposition. It'll be either 2 things. It will either be ax, along with our temporary qubits being 0, or our temporary qubits are not going to be 0, and we're going to get some garbage state that I'm going to denote bottom. We don't want that garbage state. We want to get rid of it, and the way that we'll do that is by performing a measurement. We're going to measure our temporary qubits. If they come back all 0, we know we're good. If they come back non-zero, we have to start over from scratch. And the number of times that we have to start over turns out to be proportional to alpha. Right? So alpha, subnormalization, is not just a technical little thing. It's actually directly proportional to how slow these programs are. All right, so this is the basis of our language design. Once again, we're going to start with these unitary gates. Those are our base case. And inductively, we're going to add these operators here that enable us to compose these matrices together. And eventually, you get a whole bunch of semantics that you can look at in the paper. Okay, that defines you the language. All right. So that's what the language looks like. Let's talk about how to make this language efficient, right? How to close this efficiency gap. First, we have to talk about how to measure the costs of these programs at all. One thing we could do is count the number of gates. In this case, to simplify things, we'll just count the number of x's and y's. We'll leave everything else as a footnote. Now, the thing is, as I just said, it's not just the number of gates that matters. It's also the number of repetitions of the program. This subnormalization says we have to multiply all of our costs by alpha. We're essentially repeating this whole process. So our actual cost is going to be the number of gates of the circuit multiplied by this subnormalization. That's the thing that we're going to have to minimize. The good news is that it's not too hard to compute these subnormalizations. Indeed, prior work gives us some ways of essentially just inductively going through a computation, just calculating it all, and we can figure out exactly how many repetitions of the program that we need by looking at the program. This is a very simple example that kind of gives you the idea. In our full paper, you can see the cost model of how to do this. There's actually some kind of intricate math involved with polynomials. Please ask me offline if you're curious about how all of this works. Unfortunately, I'm a little short on time. I'll take questions at the end. So in order to reduce the cost of these programs, then what can we do? Well, it's a simple idea. We're just going to combine some like terms. We're going to make these programs shorter, which is going to end up having the effect of reducing the subnormalization. Right? So this is a really great idea. And you can see that by doing this, you just get a shorter circuit. Shorter program, shorter circuit, right? It's pretty logical. But does this idea have limits? Okay, so here's another program from a different application. It corresponds to this circuit. By looking at it, you can kind of see, okay, maybe we can combine some like terms. And here is what happens. Right? You get a shorter program, but you actually do not get a shorter circuit. That's kind of surprising. Why is that? Well, partly because the idea of subexpression reuse no longer works on the quantum computer. Think about this expression. Classically, we can evaluate this expression by just performing one addition instead of two. You take a plus b, you square that, and you're done. But the quantum circuit has to perform both additions. It's just like a whole bunch of things one after the other. And even worse, right, if we're talking about things like exponentiation, right, the circuit is actually really disadvantaged because it can't cache and reuse anything. All right. This doesn't mean that we are completely hosed. There is some deep math that we can tap into here. There's something called the quantum singular value transformation that I absolutely do not have time to explain. But a way to think about it is that we can exploit some linear algebraic structure, kind of analogous to diagonalization, right? Exponentiating a matrix is a lot easier if you just want to exponentiate the diagonal instead. This gives us some really good theoretical properties, but it requires, believe it or not, a whole lot of PL work because we have to do things like constrain the properties of the matrix and the polynomials of the matrix, and we have to figure out whether these exponents exist in the first place. All right, so the bottom line is we are able to build these things into our type system and a system of program level rewrites. We ultimately make it so that we have an intermediate representation that efficiently captures what's going on in this program and generates a much shorter circuit. And if it looks easy, well, it's really not because there's a whole bunch of stuff that we had to do in the paper. So just to finish up real quick, you know, the evaluation shows that our system is able to accelerate a whole bunch of interesting programs. And moreover, it's able to outperform some of the generic circuit optimizers that, like I said, are fundamentally solving a harder job, so this shouldn't really be surprising. I want to end the paper on this final note. You know, I don't want to claim that we are ready to replace the classical linear algebra and high-performance computing stack, right? This is really just the beginning. But what I think that it is a call to action for the programming languages community. Because what we have seen in quantum computing in the last 5 years is tremendous progress in hardware and in algorithms. The software has yet to catch up. And there's a really great opportunity here for us to build better abstractions so that we can better write, verify, and reason about these programs. So with that, there is some code available. Happy to take any questions.
All right, so take a few questions here. And also for all of the people that spoke in this session, if you can just stick around afterward a little bit in case people have other questions, that would be great.
So I feel like the alpha rescaler that appeared and that you talked about for a little bit is really important towards the question of summation and the question of running time in a way that is not clear to me. Is there any sort of intuition you can give there?
Yeah, it's really surprising, right? Because it seems as if it's just like a technical factor that goes in there. But, I mean, at least you can look at the math. I mean, Robert, hopefully this math will give you a little bit of intuition because the alpha, here I wrote B of A, but technically it's actually B of A over alpha, right? So the alpha ends up propagating over there where it becomes an amplitude, and amplitudes become probabilities. So that's why our success case ends up being linked to alpha. I wish I had something that was less mathy as an explanation. You know, let me know if you think of anything.
All right.
Yeah.
Thank you.
Take one more question.
Yeah. My question was, please go to the addition of alpha.
The addition, was that the example, this one?
Yeah.
Yeah.
I mean, the alpha equation is not optimal. So in some sense, you actually can provide some upper bound on the largest eigenvalue. And I believe this is generally hard to compute the largest eigenvalue. This is more or less like a comment.
You're absolutely right. It is an upper bound, right? Knowing nothing else about the structure of the program, this is the most that we can say about the number of iterations that you'll need. Something that I really want to do is precisely to incorporate additional information about the structure to give a less coarse upper bound.
All right, let's thank our speaker again. And if there's any, thank you for attending the quantum computing session. If there's any questions you have for our speakers that you want to take offline, you can find them up front over here. Thanks again.
Yeah, hi. So for quantum fans, tomorrow at 2:40, we'll have another quantum paper on equality saturation for quantum circuit optimizations. So please come if you are interested in that.